Yeah. So, thank you, Dr. Burnett, for having me here. I'm going to be talking about open fabrics over the verbs-based fabrics this year, and legal disclaimer first. Blah blah blah. So I've given, like, the first two slides should not be new at all. They've been reused for almost the third month, and every year I try to talk about slightly different things. And this year I realized that I actually don't have anything I can talk about. so I asked around with the Intel MPI guys and the other guys at the OFI week to see if they have topics that I could talk about and if they have any data that I could share. So this talk is mainly going to be focusing around the work that's been done in the OFI week by Sean and others from the Intel MPI group to basically optimize the status of OFI on verbs-based fabrics. So you guys have seen this slide before. With the main goal of open fabric interfaces is to be an open source implementation, which is implementation agnostic of the underlying fabrics, and be designed to be more application centric as opposed to device centric. This is a current state of the union right now. A bunch of applications that exist on top of LibFabric. Actually, this is we're starting to run out of space here. Just a couple of just 1 month ago, I saw that someone from Oak Ridge and Wacom, who was also a graduate from Ohio State, they have implemented a version of OpenSHMEM over LibFabric, which I thought was, I mean, it just happened. So I mean, this list is keeping on growing. And the other new thing in this slide that was not there last year was this Intel MLSL, which is our machine learning and scalable machine learning scaling library, which is really designed to be an application level fit for the deep learning type of applications. And I've already mentioned a bunch of providers underneath, and there are a couple of other providers that are not listed here. I think Brian Barrett from Amazon mentioned that they are going to do a LibFabric provider at some point, and there are some others in the works. But as I said, this year it's mainly a presentation on the implementation status and where we are. So in 2017 we had up to version 1.5.3, and in 2018 we are working on the 1.6 releases. What are some of the things that are featured in the 1.6 is basically the provider infrastructure is starting to become more and more filled out with more and more utilities that different network providers can use. And there's a PSN2 native provider that is coming in 1.6. I personally don't know much about that, but if you have any questions, I'm happy to forward those questions out. And I'm going to be talking about the rest of these bullets in the rest of the talk. And in 1.7, which is our next release series, there will be the new providers which I mentioned in the previous slide, some new utility providers and shared memory and other API enhancements. The provider infrastructure updates. So the way LibFabric is being structured is actually trying to be broken down into smaller and more generic pieces for LibFabric providers that don't implement the full subset of the APIs that LibFabric exposes. So this is a nomenclature that we came up with. It's called RxM, which means reliable datagrams over connection-oriented transport. So what do I mean by connection-oriented transport? Say like a Verbs reliable connection is a connection-oriented. Windows will have Network Direct. You have TCP. You can have others too. So we have this generic entity called RxM, which emulates a reliable datagram endpoint, which is RDM, over a bunch of like a message endpoints. So really, in terms of MPI development, and like certainly from Mbappé's group, this is nothing new. This is basically a form of on-demand connections. And what is a little bit unique about this is that none of these layers really assume the underlying API underneath it. So like this RxM layer doesn't really expect to see verbs underneath it. It can literally be anything. So this layering is kind of unique and is a bit more generic, that allows the fabric vendor to quickly come in and like utilize this component. So I'm going to talk about some code path measurements that I did. So as I said, this stack is beginning to be put together, and we're starting to look at the optimization of this. So like one of the questions that we always had was that, what is the software overhead if you want to go from MPI send through to the libfabric and back, and what does that look like? Does it add more overhead or not? So I did this experiment like late last month after ISC. And here I'm trying to measure in the ping pong test, which is the OFI latency test, you guys know. So suppose you start an MPI send, and then you have to execute some amount of code, and then you go to Verbs or whatever underlying library, and then you send the ping message out, and then you actually have to process the receive, and then have some Verbs path again to like actually send the pong message out. So let's ignoring the Verbs path. Let's just look at what is the MPI and fabric path. So for Mbappé, it will be the full Mbappé path, where you go from MPI to basically the Vibe verbs. And for say MPI over libfabric, it will be MPI plus libfabric and then onto verbs. So I started to look at what is the send path. So I measured. Where's Dr. Pan? Dr. Paris? Since he asked us to give some challenges, so this slide was supposed to be a challenge for him. So I'll connect with him later. So what we are seeing is that even though you're theoretically going through another layer, but the fact is that a lot of these layer optimizations are very small, and so Dr. Manu, this is the challenge that you asked for. Okay. So I'm presenting for his benefit. I'm going to show what I'm presenting again. So I'm trying to show the software overhead to go from MPI send to the fabric, and then onto verbs. But I'm not really measuring the verbs. Then I'm saying that same thing on the receive side. So here I'm measuring both the Mbappé, like the RDMA fast path and the SRQ path, and I'm measuring the MPitch. This is the CH4 path. So broadly, what I started off by seeing, like, is there any extra overhead in going through libfabric to go to verbs? That was my initial motivation. What I found out was that right now we don't see that difference, at least with the Mbappé. And what I'm seeing is that really like the CH4 is what is giving a lot of the benefits here. And maybe Hari, with you, I can probably sit down and show you the full data at some point. Go ahead.
Do you accept hard questions now or after?
Oh, anytime.
And how many cycles each instruction?
I mean, the instruction mix is very similar. But
like if you hit huge caching, it's like hundreds of nanoseconds.
Right. So I'm not. So this is the first step, because people were saying, oh yeah, you have to go through left fabric to go through work. So is that true? And then secondly, the question becomes, okay, at the end of the day, everybody just cares about latency and bandwidth. So I'm going to go there. But this is the first thing that I wanted to actually mention and sort of present it as a challenge, because CH3 has been stagnant for many, many years. And the CH4, they have actually removed a lot of the bulk, and especially you can see the receive path is where they actually benefit. And when I look at the instructions stream, I look at, actually this is also not optimal. Like the send, you should be able to be around 250 to 60, and on the receive, definitely less than 500. I still see a bunch of places where things can be optimized, and not just for the fabric thing. The same thing is also possible for MPI. Like Mbappage, because it's just MPI or InfiniBand, right? So then it comes to the latency. So here I took, and by I mean somebody from the Intel MPI team, took the latest Intel MPI 2019 beta update one. I think this is publicly available now, and the OFI master, tip of the head right now. And this is showing a relative latency with the OSC latency. So the dark blue line is just Mbappage, and obviously lower is better because it is the latency. So you can see that it's roughly the same for the small messages. A teeny tiny bit overhead, and I think this is because some of the receive descriptor posting is still not fully optimized. But here, for the medium-sized messages, we saw a decent improvement with one of the new protocols that was invented by an engineer, which is, Mbappage also has this. It's called, it's the R3 protocol type. One in the lib fabric world, they're just calling it segmentation and reassembly, but it's a very similar thing. But it's not on by default, but the lib fabric people actually have on that on by default. So, broadly again, the thing is.
So does PSN2 have support for this?
This is all about verbs. This entire talk is about verbs.
Oh, verbs.
So you missed the title slide.
Yeah.
So I'm not talking about PSN at all here. Just talking about. And the platform is mentioned. It's a pretty standard platform. Then we look at the messaging rate, and actually this is where the code path enhancements really start to show up, because in the messaging rate, what ends up happening is that your network is fully saturated because you sent a bunch of messages, and your network is fully full. So any differences in the software that's running on the CPU basically shows up. And here we saw a pretty easily measurable performance gain. And for the large messages, here again, I don't know exactly what's happening. I'll have to get together with the INPI guys to see why it's not flat. So ideally, we were going to be happy if it was flat throughout, but it turns out that CH4 has actually given us a lot of good benefits. And the rest of the talk is more about other utility providers. So in this slide, I'm showing a reliable datagram over unreliable datagram. So this is again in terms of Mbappage, this is the UD mode. So if you had to do scaling on a fabric that was not scalable or could only scale with UD, then you would do this. Like the Verbs UD are in case of the Cisco USNIC, which is simply like a UD NIC, or simply like UDP socket. So you could have the same RDM, like this RxD components sit over multiple of these fabrics. It doesn't really expect to see a Verbs UD. It can run over other types of UD as well. Shared memory, again, nothing particularly new from the Mbappage point of view, but other than to mention that this is also possible now within the fabric. So there are two ways shared memory can be used within the fabric. One is it can be a standalone provider, or it could be a full OFI provider that can choose to import the shared memory features from this shared memory code. Again, the goal is to increase the code reuse so that we don't keep reinventing one shared memory module for one fabric, another shared memory for another fabric, and so on. And we took a look at the Envapage research that has been done, and I think the underlying design has ended up to be fairly scalable. I think it currently works with the CMA, and I think XPMM they're exploring. One of the problems with XPMM is that in order to get access to it, it's not, because it's like usually on the Cray system, so that's why it's still under development. And this is again the memory registration caching. This is again all of these components exist within Envapage, because all of these are the type of things that you have to do. Now again, if you have on-demand paging and things like that, this stuff will just go away. But in the meanwhile, if you don't have on-demand paging, then you need to do similar type of things. One of the pain points of memory registration is that there is no generic solution to actually give you a notification if the page mapping is changed, and that's been a standard issue for many years, and so that continues to exist. So one thing we added was a performance monitoring framework inside it. So if you want to use any device specific or like a CPU instructions for getting basically your CPU counters or processor counters, then you can basically request it, and you could use these from tools outside of LibFabric, but what this mode brings to you is that to actually have a fine-grained understanding of what happened with the CPU or whatever processor during the scope of my LibFabric call. So that type of scoping is sometimes not so easy to get from other tools, because if you're just measuring with some other tool, then what can happen is that you'll just measure all the cycles or the cache misses or whatever, and they can show up in all parts of the code, like in the send path and then in the receive path while you're polling and looking for messages. You can just get a lot of mixed signals there, and this framework allows you to finally use this tool in specific parts, and makes it easier for say an MPI to find out stuff. This is another part that we use to enhance our tool interface. This is called, what we call is the hooking provider. LibFabric is based on a bunch of function pointers, so that when you call a LibFabric function, it just goes to the function pointer that was initialized at the runtime. So this hook can be installed when you say initialize or open an endpoint or something like that. You can initialize a hook, and it can basically replace your function pointers, and then it can use to intercept any call that you want. And right now, I think the hooking provider is doing some basic debugging, but it's like a generic framework. It can be used for anything, and this is always enabled and doesn't cause any extra overhead, because as I said, it's a function pointer based system. So if you go. So one debugging thing is a full debug. So one can imagine a situation where you want to verify all the input arguments to a function. But you don't want to do that on your performance build, right? So it could just go check every argument by saying it's null or not. It could install debug hooks, and it's pretty extensible, so you can write whatever you want. That's a good suggestion. We could add something like that. Performance analysis is one more thing. If you want to start some counter or something like that, then you could use a hook basically. And MPI does this with the weak symbol intercept, which if you were not born in the 70s, you probably don't know what a weak symbol is. But this is like a modern version of a weak symbol. Multi-rail, again, nothing very unique with respect to what NVAPage already has. You have multiple endpoints available, then you could have a generic component that sits on top of it and gives you multi-rail. And the uniqueness is like, so this multi-rail provider is basically another OFI application almost. So it is like using just the simple OFI APIs. So again, like when we are going ahead and designing these layers, we're trying to make these things as generic and as reusable as possible, because over time, fabrics are going to come and go, and all types of technology is going to change. You don't want to be reinventing these. Like reinventing this is already a lot of work. So the multi-rail provider is simply another OFI application. And we're looking at to see if the multi-rail provider can be used for recovery fallback. So if like one of the rails failed, can you go to the other one? And I think our research group, NVAPage, also looked at this in the past. And now about some things that are going on for 1.7. We have a persistent memory API that we are investigating with respect to, with collaboration with SNIA, which is the Storage Network Industry Association. I think the broad idea is that you can define persistent memory regions, and you just have a new completion semantic by saying that I'm submitting this write operation. Let me know when it's actually committed, not when it's actually transmitted, but when it's actually committed into the remote memory. So then you could have this type of semantic, and you're looking at the exploration of whether it can make this byte addressable, and whether this can support atomics or not. Data domains. Now, as like Gilad mentioned, there's a bunch of other architectures that are coming, like FPGAs and SmartNICs, and where you don't have, you could have, so the domain where the processor and the fabric are being, where you can do load store is actually changing, right? Earlier you could do CPU and memory. Now with the persistent mem, you can sometimes do load store, but if there are incoming data from the fabric, you need to sync with the CPU. And then you have some SmartNICs, so that's a different domain. So we're trying to define these domain boundaries so that an application, when they are writing, they can request for what domains they want. So if you know what domains you need and you have multiple different implementations underneath it, you can query by that request. Like if your application actually relies on having load store access to the persistent memory, so you can request that type of system programmatically. Then this variable length messages, which is also another API feature that we're thinking of adding. Looking at a bunch of applications, it looked like this eager rendezvous protocol was being invented and reinvented at so many layers. I'm not even go through the slides. Like all these applications are basically trying to reinvent this, which MPI already has, and we have absorbed it under libfabric with the tag matching interface. So everybody was reinventing this, and Sean said that not many people know how to spell rendezvous. So if we make a right abstraction, then maybe only one person has to figure out how to spell rendezvous, and then the other people can just send and receive messages. So in this model, what ends up happening is that if you don't know how much data you are receiving at the receiver end, so the sender can just say that this is a variable size message, and then the receiver can look at the completion and decide what to do, whether they want to accept the message, discard it, and this is opt-in, and this further takes the protocol further down into the libfabric layer. So certain providers may be able to absorb a lot of these exchanges with just network level acknowledgements and not have any software at all. And we're also looking for HPC applications where there's a bunch of load balancing and stuff like that. And this has been a problem generically for distributed task stealing, is that if you're trying to take work from already busy server, so the poor server is already busy and you're trying to steal work from it, it doesn't have. So like suppose one of the processes could say that I'm going to be busy for a while, and it can set a flag and then go do a bunch of compute stuff, and then in the meanwhile, if processes are trying to actually contact that busy process, they would get a busy signal back. And if there's a way to actually offload that into the network libraries. Last couple of slides are companion APIs that go along with libfabric. So there are some folks at the OFI WIG who are working on C++ standardization. They're trying to define a C++ API that would be under the communication standard, and they are trying to model it directly on top of OFI. It's called ASIO. If you guys are aware, you can check the ASIO model. So this will allow applications that don't want to learn too much about the low-level, programming of libfabric or whatever. If they want to stay at the C++ layer, they can just use it. And the other thing that we are trying to work on is Rsockets. So right now, Rsockets is part of librd_acm, and it depends on Verbs directly. Now we're trying to move that on top of OFI, which is called lib_Rsockets. So that means that it can work on a bunch of different fabrics, and fabrics can actually reinvent the Rsocket protocol if they want. And actually, one of the interesting things that is happening is that this is being considered for integration into the OpenJDK, which is basically a Java JVM. And the cool thing is that if you are inside the JVM, you don't have to use the LD preload hacky technique because the JVM can just redirect all socket calls to the Rsocket call. So think of like all that cloud middleware that is actually written with Java or Scala or runs within a JVM. And one of the problems that we've been facing for a long time is how to get them onto the high performance fabric. This is a absolutely zero-touch effort to get them onto other fabric. Now, they're still not optimal. They're still using the socket interface and the streaming semantic. And there's a big gap between the streaming semantic and the underlying hardware. But still, it's a lot better than where we were. So I'm personally most excited about this. So in summary, I described a bunch of the software work right now that is going on to complete the OFI feature set on a wide variety of fabrics that don't have, are not implementing the entire set, because the API set was defined by what applications need. And the components are very generic and completely reusable, and fabric vendors are actually pretty excited because they get to implement only a small subset of the features, and they get the software framework all around it. And an OFI application can just work. Again, it's not anything different than the MPI device model, right? Where you have a vendor just needs to implement the small part, and then the rest of it they get, and they can optimize whatever part they want, and you're free to participate in OFI. That's it.